You type 12 words into a box. A few seconds later, an answer appears as if it came from nowhere. But it came from a factory, one filled with machines, cooling pipes, batteries, transformers, and enough electrical equipment to make a small power station feel underdressed. We call it the cloud, which is excellent branding. Clouds are light, clouds float. Clouds rarely require their own substation. AI does. Behind the clean interface is an industrial system, and its next great bottleneck may not be the model or even the chip. It may be something much older, finding enough electricity to switch the machines on. One ordinary text request is not an environmental apocalypse in miniature. The International Energy Agency says simple text tasks have become much more efficient. The larger problem is scale, more users, longer reasoning, video generation, and agents doing many steps instead of one. Efficiency is improving. Demand is growing faster. Start with a server rack. It is roughly the size of a large refrigerator, except it is full of specialized processors and has no interest in your leftovers. The IEA says AA server power density increased 11-fold between 2020 and 2025. By 2027, one advanced rack could have peak demand comparable to 65 households. Now place hundreds or thousands of them together. The question is no longer, how do we power a computer? It is, how do we feed an electrical neighborhood packed into one building? The chips are only the center of the machine. Electricity arrives at high voltage. Transformers step it down. Switchgear routes it. Batteries and backup systems protect it, and then nearly all that electricity becomes heat. So pumps, fans, and heat exchangers move the heat away before the processors cook themselves. Servers average around 60% of electricity demand in a modern data center. The rest is the life support system keeping them alive. The cloud, as it turns out, has a loading dock, a cooling plant, and a room full of circuit breakers. Large data centers used to be discussed in tens or hundreds of megawatts. Now the plans are entering gigawatts. OpenAI announced a 1.2 gigawatt lease for one Texas site within a much larger infrastructure program. A gigawatt is 1 billion watts, roughly the output of a large nuclear reactor. That does not mean the site already draws that amount continuously. Planned capacity is not present consumption, but the direction is clear. AI companies are no longer shopping only for chips. They are shopping for power systems. And here is the strange reversal. The glamorous bottleneck is the chip. The practical bottleneck may be the transformer. A processor can be installed in a rack, but the rack still needs switchgear, a substation, transmission capacity, and a grid connection that may take years to approve and build. The IEA estimates grid constraints could delay around 20% of planned global data center capacity through 2030. Imagine spending billions on the most advanced computing machinery ever built, and then waiting because the local electrical system cannot safely plug it in. The future of artificial intelligence may depend on some of engineering's least fashionable objects: large metal boxes, copper windings, and permits. Globally, data centers remain a minority of electricity use. Locally, one can arrive like an industrial plant, large, concentrated, and faster to propose than the generation and transmission built to serve it. The IEA's central outlook has global data center electricity consumption rising from 485 terawatt-hours in 2025 to about 950 by 2030. In the United States, Lawrence Berkeley National Laboratory estimates data centers could use roughly 1/10 or more of national electricity by 2030, depending on how growth unfolds. Those are projections, not destiny. But utilities must plan before they know which enormous projects will be completed, how full they will become, or how steadily they will run. Build too little, and projects wait. Build too much for projects that never arrive, and someone may still pay for the infrastructure. So what powers an AI factory? There is no single answer. The IEA expects renewables to meet nearly half the growth in data center demand through 2030. Gas and coal are also expected to supply more than 40% of the additional demand in the near term. Technology companies are backing nuclear, geothermal, batteries, and direct power agreements. But a contract and a power socket are not the same thing. The electrons entering the building still come from the physical mix of the local grid. Then there is heat. Packing more computing into each rack means moving more heat away from the chips. Some facilities use evaporative cooling. Others use closed-loop liquid systems, outside air, or combinations that change with the weather. This is why one AI prompt uses this many liters of water is usually a bad universal claim. A Lawrence Berkeley study found workload-level water use can vary by more than 10,000 times depending on the server, utilization, grid, climate, and cooling design. The useful conclusion is not one dramatic number. It is that location and engineering choices matter enormously. A giant new electrical customer can create real local tension, transmission lines, generation, water planning, land use, and the question of who pays. But a data center is not necessarily a helpless block of demand. Batteries can smooth rapid changes. Some computing can move to another hour or location. Flexible connection agreements can reduce load when the grid is under stress. The same facilities creating a grid challenge may also become unusually controllable industrial loads, if the rules and incentives make that worthwhile. That is the real physical story behind AI, not that every question drains a reservoir, not that the cloud is about to consume all electricity, and not that efficiency will magically erase demand. The story is a race between two clocks. Models, chips, and investment move at software speed. Power plants, transmission lines, substations, equipment factories, and permits move at infrastructure speed. AI may feel weightless on the screen. Its expansion is becoming one of the most physical construction programs on Earth. The chips may be intelligent. The grid is still built one transformer at a time. AI is forcing electricity systems to grow. But growth is only half the problem. A grid must also remain balanced every second, because when voltage control, generation, and safeguards fall out of step, two countries can go dark in about 90 seconds.